All right. So you guys have done the assignment. In case you didn't notice, I uploaded back the comments. There is no grade associated with it. Don't stop what you're doing now to go look at it. It's whether or not you did it and you did it seriously. You got 1 mark. If you didn't, hand it in. Or if you didn't do it seriously, you didn't get the mark. So two. Um, the theory behind it is actually quite, in my opinion, fun to do because it's very intuitive. And it requires us to know a little bit about what it means to put batteries in series and parallel. So we'll just go through that real quickly. You guys did the research here. When you put batteries in series, what happens to the voltage? You just add them up. All right, so you can say that in series, V total is equal to V1 plus V2 plus V, etc. if there is more. So you can write that down as a summation. So V total is equal to the sum of all voltages I from n is equal to 1 to I. Sorry, I got it backwards. From I is equal to 1 to n. All right, that's pretty straightforward. Later on, when you guys are doing circuits, you'll be playing with the batteries and the bulbs. All that stuff is over there. Just take some batteries and put them next to each other and see what happens. Alternatively, in parallel, the voltage doesn't add up. All right. So in this case, V total is equal to V1 or V2 or V3, etc., etc. Okay? And this is in parallel. You guys talked about something called longevity, and we're going to talk about longevity as well today, and we're going to quantify longevity. How long does it take for something to get depleted? Here are the two examples that we're going to look at. I mean, this is one of them, and then the second one is going to be in series. But here it is. You got two batteries in parallel powering one light bulb versus one battery and one light bulb. Right? We're going to compare those two situations. And what we're going to look for is that when you add a battery in parallel, the brightness of the bulb is not going to change, right? So brightness does not vary. What we're going to be looking for is for longevity of the cell to increase, all right? So the battery's going to last longer, but the brightness won't go up, okay? What I want to just plant a seed in your minds right now is just think about batteries as having a certain amount of charge, okay? We talked about charge when we did static electricity. This is the exact same kind of charge that I'm talking about. So let's say we have one battery. A one battery should have a charge of Q. The two equal batteries should have a charge of how much? 2Q. Exactly. So here the battery would be 2Q. Right? How we use this charge is going to be different based on if we use parallel or series circuits, right? But the point is that we have now available to us 2Qs. So there is an advantage of adding a second battery, so we're doubling the charge. And the same thing in series. If we had one battery, it would have a charge of Q. If I had two batteries, what would be my charge? How many charges do I have in total? Doesn't matter how they're plugged in. I have 2Q, yeah. Right? Again, it's going to be how we wire it is how we use those charges, all right? But what we really need to know is that there is 2Q available to us no matter how we plug them, whether it's series or in parallel. And what we're looking for to see here is the brightness of the lamp increases, right? And the longevity of each cell does not change. Okay, that's the important part. It does not change. It doesn't decrease. It just doesn't change. Okay, so we're going to remember those two things. We're going to go and do in some math now. Any questions on this? For brightness, we're going to need to know about power. Power, and it's measured in watts. It's got a relationship equal to I squared R. That's the one that we're going to use mostly. But it can also be considered as I voltage. And this is going to be the current passing through the bulb. And V is going to be the voltage drop of the bulb. And R is going to be the resistance of the bulb. Okay? Units are watts. The symbol for that is a big capital W. So here we are. Let's do some math. Before I go into that series circuit, I just want to go with it when there's just one battery. So here I have a circuit that has one battery, one bulb. The battery is 5 volts. The resistor or the bulb is 20 ohms. If I wanted to calculate the current, that's pretty easy for me to do. It's Ohm's law, V equals IR, and 5 volts equal to I times 20, and therefore I is equal to 0.5. Is that it? No. 5 divided by 20 is what? 0.025? Is that right? No. 0.25. It's just 0.25, right? Great. So I know that the current going into my light bulb, the current going into my light bulb is 0.25 amps. The current coming out of the battery, because it's in series, must also be equal to 0.25 amps because it's got nowhere else to come from. All right, so if you follow back this line, right, it's always going to be, no matter where you look at on the circuit, it's going to be 0.25 amps. So if it's 0.25 amps, it's everywhere. That's what the battery is getting consumed at. Okay, we're going to talk about consumption. I'll remind you that the charge here is Q. And now let's go talk about this this circuit with two batteries in it. So what's the voltage here? If I have two series batteries of 5 volts each, 10 volts. Okay, so my V is equal to 10 volts. My R is staying the same at 20 ohms, and therefore I can calculate my current, which is going to be 10 volts is equal to I times 20 ohms, and I is going to be equal to 0.5 amps. All right, so let's draw it again. There's going to be 0.5 amps going into my light bulb. There, look at that. It's got nowhere else to come from other than those two batteries. So that means there's going to be a 0.5 amp current passing through each of those batteries. And if I were to calculate the power of my original light bulb when I had only one battery, I can easily do that because P is equal to I squared R, which is going to be equal to 0.25 squared times 20 ohms. That's going to give me 1 over 16 times 20. Can someone do that for me? 1.25? It's going to give me 1.25 watts. And if I were to calculate my power here, or my brightness, would be 0.5 squared times 20. And that's equal to what? 5 watts. Right? So if I'm comparing my brightness here, I've added a battery and I've quadrupled my brightness. That's pretty good. I got something out of adding a second battery. So this is going to be 4x brighter. Yeah, 4 times brighter. Perfect. Let's talk about longevity now. All right. Before we talk about actually calculating longevity, I'm just going to remind you real quick, this circuit here on the left, we said has 2Q charge, right? And we also have to remember what the definition of a current is. What was current again? You guys remember what that meant? Yeah. It's what? Flowing charges. And if you were to give it a unit other than amps, because amp is kind of arbitrary, we just called it that after a person. What is an amp? 1 amp. Yeah, it's how many coulombs are traveling per second. Or if it's 1 amp, it's 1 coulomb of charge traveling per second. So, okay, so in the first case, right, Q, if we divided this by time, because that's what our longevity is, right, that'll give us the current. Right, if we assume that the current is constant, we're going to assume that the current is constant. How long it takes for that charge to deplete is going to be the longevity of that battery. All right, and in this case, I have 1Q, right? Let me just go back for a second. In this first situation, the current is what compared to the current when you add a battery? It's a pretty, yeah? It's just exactly half. All right, so you add a second battery in series, you're doubling the current. Okay, so in this first situation, I only have 1Q, and I only have 1I, right, because it's going to be 2I in the other situation, and therefore the time is going to be equal to Q over the current. Yeah, no way. All right, so the time it takes is going to be that. That's for the first case. But in the second case, you have 2Q divided by time, but this time you have double the current. So the 2's, they cancel each other out, and T again is equal to Q over I. So in both cases, it doesn't matter that there is a second battery. The longevity is the same. You're not increasing how fast the batteries die by adding a second battery. It's the same. Same longevity. Any questions on that? Let's try to do this with a parallel circuit. I'm not gonna redo the one battery system, but I'm just gonna remind you that the power was equal to 1.25 watts. The current was equal to 0.25 amps. And that was the current that was going through the battery. Okay, so we're gonna do the same thing in this situation. What's my total voltage of this circuit here? How much? 5. My resistor, oops, not I, but R. My resistor is 20 ohms. And I can calculate my current going into my resistor. It's going to be 0.25 amps. All right, and that's this current going here, 0.25 amps. We can calculate the brightness because P is equal to I squared R. It's going to be 0.25 squared multiplied by 20. And we already calculated that. It's going to be 1.25 watts. Same brightness. Oops. 1.25 watts, 1.25 watts. Right? The brightness didn't change. I have the same kind of situation. Let's look at the current coming from each battery. So this 0.25 amp current is coming in from this node. That's just the amount of current that's passing through this light bulb. But that current started from these two batteries, and these two batteries are equal. So that means that the current coming out of each one has to be equal. And when they come and meet together at this node here, so they're going to come from here, and this is going to come from here, and it's going to meet together. When they meet together, it's 0.25. So what does each one provide? How much? You guys can do that in your head, right? 0.125 amps. So each battery is only using half the amount of current. And so let's look at longevity again. So in the first situation, we said that Q over T is going to be equal to I, and therefore T is going to be equal to Q over I. And each one of these batteries has Q charge. And let's say there is this current is specific for this 1 Q charge battery, then I can say that for my second situation, for 1 Q charge, I have 0.5 I, right? Because the current is actually half. This current is half of what it was in if it didn't have a second battery. So if that were the case, then if I were to just isolate time, so T is equal to Q over 0.5 I, or I can say I can bring the 0.5 up to the top, so it would be 2 times Q over I. So what's happening to the longevity of my battery? It's what? Increasing by a factor of what? 2, exactly. So battery longevity doubles. Yep. Yeah, that's what I did, actually. These two are equal. Yeah, you could. Yeah, because then I would use the total battery, and I still have the total current, and I would have 2Q instead of just. Does that make sense? Yep. Battery longevity doubles. All right, that's pretty straightforward. Let's do some examples now. We'll do this one together. Here's a very simple circuit. This time we're adding bulbs. So as more and more lamps are added in parallel, what happens to the brightness of the bulb? So let's just calculate what the brightness of the bulb is right now. So V is equal to I times R. So 1.5 is equal to I times 3 ohms. And therefore I is equal to 0.5 amps. If I is equal to 0.5 amps, that's the current passing through it. And we can calculate power for I squared R. And I squared R is going to be 0.5 squared times 3, which is going to be equal to 0.75 watts. That's the brightness if only one battery existed. If I had two light bulbs, I'm going to redraw the circuit. .5 volts, 3 ohms, 3 ohms. So I've added a light bulb, same resistance. What do I need to do to find the current that goes through it? It's kind of like the quiz that you guys just did. What do I need to do? What do you need to do? Yeah, correct. How do I know what's the current coming out of the battery? How do I figure that out? I need to find total resistance. Okay, good. So if I need to find total resistance, it's two 3 ohm resistors, and that's an easy one. 1 over 3 plus 1 over 3 is equal to 2 over 3, and 3 over, and then you reverse that, so it's 3 over 2. So that's 1.5 ohms, right? So Req is equal to 1.5 ohms. Voltage is 1.5 volts, and therefore current is going to be equal to what? 1 amp. That means now there is 1 amp current coming out of the battery. There's a 1.5 volt drop for each bulb because it's in parallel, and therefore the current going in each, about 1 amp going into this node, right? That means it's going to be split evenly because my resistors are equal. So what's going to be the current in each resistor? 0.5, yeah, exactly. So is it the same? So here we said that the current going into the light bulb is 0.5. Here we said the current going into the light bulb is 0.5 and 0.5. So what happens to the brightness of these two light bulbs if the current doesn't actually change? It stays the same. Brightness stays the same. How about the currents leaving the battery? Does it stay the same? No. So the current increases. If the current increases, the current coming out of the battery, then what happens to the longevity of the battery? Decreases. All right. Let's do another example. This time there are two batteries. I'm asking you the same exact questions, but this time there are two batteries. So let's do some math and figure things out. Let's find the brightness of one light bulb. Could you guys do that actually? Determine the brightness of that one light bulb when there's two batteries and only one light bulb. Try to figure out what the brightness is, okay? Remember, brightness is going to be power. If you want to calculate power, you need current. So you guys work on it. I'll work on it. Don't look at the board. So here's a trick for this problem. It's not really a trick, it's just something that you have to keep remembering to do. So here we calculated that the current entering the bulb is 0.25 amps. Here when we calculated using REQ, because there are two in parallel, we calculated 0.5 amps. You have to remember, and I also forgot it when I was solving the problems there earlier, you have to remember that, yeah, it's when these two combine, you're going to get 0.5 amps. And that's what's going into the equivalent resistor, not into each resistor, because it has to split up again. And if it has to split up again, then it goes back into 0.25 amps. So in fact, what you can say is there's 0.25 amps coming out of this one, 0.25 amps coming out of this one. They combine to make 5 amps. Then they go, oh, there's a node here, and then they split up again to 0.25 and 0.25. In this case, because the resistors are equal. Okay? You have to remember that the amperage that you get for the REQ is not what's going into each resistor, it's what's going into each resistor if it were just one big resistor, and then you have to split it up again if it's in parallel. So in the end, what you see is that the brightness doesn't change, and that's what we figured out earlier. So that follows consistently with what we thought. So the brightness stays the same. The current leaving the batteries are going to be double. So here the battery, if this is 0.25 amps, then that means that each battery here is giving 0.125 amps, and here each one is giving 0.25 amps. So the current increase, right, and the longevity therefore decrease. All right, the next one you guys are going to do on your own. It's a bit more complicated. There's just one point of convention that I want to tell you. When the question says the switch is closed, it means that the circuit is complete. This is a closed switch. Open switch is when the switch is not complete. Okay? So that's a closed switch and that's an open switch. I'll write that on the side. Yeah. So if I were to say turn on the lights, are you closing the switch or opening the switch? You're closing the switch. Counterintuitive. I'd like you to use math to solve this problem. Okay? It's easy to reason it out, but really math is the one that gets you to solve. What's the answer for the first one? Yeah. 0.1875 for the brightness. Okay. And does that with one battery or two batteries? And what is it with two batteries? What is it with one battery? If you want to know if the brightness increases or changes or whatever. Name shows, exactly, right? Because you're just adding a second battery in parallel. That's the reasoning part. You're adding a second battery in parallel, and therefore you're not increasing the total voltage, and the current passing through here is going to be the same. And therefore, the brightness does not change. You can calculate the power in both situations, and you'll see that it doesn't change. Brightness stays the same. This is so buggy, it's annoying. Brightness stays the same. Yeah. This is about 0 point. Anyone else disagree or agree? Okay. All right, perfect. What's going to happen to the longevity of the circuit? It's going to what? Increase. Longevity increases. We know that because you added a battery in parallel. All right, C. Switch 2 remains closed, and now we're going to close switch 1. Now what happens to the brightness of L1 and L2? All right, okay, well, this is going to be tricky. So let's figure out what the brightness is going to be for each of these. You guys said it's 0.1875 watts for each. Right, now we're going to close switch 1. So that means that our REQ is going to be different, right? We have a new total resistance. What's going to be the new total resistance for the whole circuit? 4.5, very good. Before, the total resistance was 6. So the resistance went down. All right, if the resistance goes down, current goes up or down? Up, exactly. So let's figure out how much, it goes up by how much. Voltage is still 1.5 volts. So 1.5 is going to be equal to I times 4.5. And therefore, I is going to be equal to 0.33 amps. Okay. 0.33 amps is the current of these two batteries combined. Okay. So what is the current passing through What is the current passing through this light bulb? Well, that one's increased, right? So let's figure out what the power is of L1. So the power of L1 is going to be equal to 0.33 squared multiplied by 3. You get 0.33 watts. Is that correct? What happened to the brightness? We said it was 0.187 watts. Here is 0.33 watts. It increased. All right. Now, now this 0.33 amps of current is going to keep going across it, and then it's going to split up into two. And these are two equal resistors, so it's going to split up equally. So the current going in each one now is going to be half of 0.33, which is 0.17, or 0.17. Yeah, so 0.17 amps going into each of these two light bulbs. Before I closed that switch, the current was 0.25. Now the current is 0.17. So this one, the brightness is going to increase or decrease? Is what? Decrease. All right, so let's just calculate the power of L2. It's going to be 0.17 squared times 3. And I have no idea how to do that in my head, so you guys will have to tell me. 0.08, I think, or something like that. What? Not newtons. Okay, so what happened to the brightness? Increase or decrease? It decreased. Okay. And now a fourth bulb is added. What's going to happen? Let's not do any math this time. If I added a fourth bulb in parallel, what's going to happen to the total currents leaving the battery? The total current is going to increase, right? But then it's going to split more. So L1 is going to, what's going to happen to L1? L1 is going to increase, and L2 and 3 are going to decrease. Okay? I don't have any room to write that, but you guys write that. Okay, great. You guys work on this? 15 minutes. Go. You guys have an answer for A? Just, I want you guys to think about it. It should be a very simple and quick one to answer. Yep. Yeah, sure. It doesn't really matter if first switch or not. It just switch to open versus switch to close. If I add a resistor in parallel, what happens to my total equivalent resistance? Decreases. Okay, so my total resistance decreases. What's going to happen to my total current? What? Increases. Okay, you remember that? These problems can be solved in 2 seconds. Okay, you increase the current whenever you decrease the resistance. Simple as that. You can solve that whole problem just using that logic. You can calculate it as well. I will ask you guys to calculate this. It's long, but it's something that you should be able to do. It's just the same that we just did with what you guys did on your quiz, except I'm asking you now to calculate power as well. All right, let's end that there.